Hello everyone and welcome again to Physical Chemistry for Life Sciences. Today we are going to continue with the kinetics chapter, and we will talk about the temperature dependence of the reaction rates, which is really an important aspect of reaction kinetics. So it was observed, generally speaking, that the rate actually increases with the temperature of the reaction. So this is general observation of most reactions. And the rate constant itself, it is temperature affected. So despite the equilibrium, both the equilibrium constant and the reaction constant actually, it's affected by temperature. So the rate constant itself, when you measure it, you can measure it at one temperature, but if you change the temperature, the rate constant the value will change itself. Now, reaction in the gas phase typically have rates that are only weakly sensitive to the temperature, and some actually reactions, like reactions in enzymes or reaction in surfaces, they have strange or odd temperature behavior, as I'm going to tell you in a few seconds. Now, the one who came up with the idea of studying reaction rates with temperature is Arrhenius. He's a very famous scientist, of course. He did a very well job, and this is Arrhenius equation. It's one of the most famous equations on reaction kinetics. It's called the Arrhenius equations. It's Kr equals A times e power minus Ea over RT. So this equation, the first one, Kr, this will tell you the exponential growth of Kr with temperature. So the first equation here, which is Kr is equal A exponential minus Ea over RT. This equation looks like a y, A is constant, Ea is constant, R is constant. This equation looks like an equation looks like A e power minus 1 over x. We know that y is equal A power e over x. This is exponential growth function. Which looks like this. If you plot, just like this is the coronavirus function, I call it, which looks like that. This is an exponential growth function, okay? And we are in the coronavirus, maybe we are somewhere here, and we don't know if it's going to continue to the growing, or maybe we're going to get a peak like that. Nobody knows. So this is called exponential growth function. It's y is equal A power e power x, and this is also an exponential growth function. A e power minus 1 over x, which is exactly e power x. So this function here, the Arrhenius equation, it's an exponential growth function. So if you plot the Kr and the y-axis, which is the rate constant, and temperature here, you will get equation like that. But this is a curve, and again, it is not good for deducing some constants of it, unless if you have a good program to do that. So that's why we integrate this equation, and we come up to the integrated form, which is ln Kr is equal ln A minus Ea over RT. In this equation here, this equation is a linear equation. So if you integrate the above equation, Kr is equal to something, so you get ln Kr is equal minus Ea over RT plus ln A. This is the linear form of the Arrhenius equation. It's widely used. It's one of the most widely used equations in chemistry right now. And this one is your y, this one is your mx, and this one is your intercept with the y-axis. And therefore, y is ln Kr, and guess what is x? Guess is 1 over t. So y is equal ln Kr, and your x is 1 over t in Kelvin minus 1, of course, in units of Kelvin minus 1. So if you plot ln Kr versus 1 over t for a given reaction, then you should obtain a slope, and the slope is equal minus Ea over R. And I think you passed through this when you did the homework 1, where you did something for the Clapeyron equation. For the classic Clapeyron equation, However, I didn't teach you that, but you figured it out that when you did the homework one, it was something like this. When Ln the pressure, you plot Ln the pressure that is equal, while my delta H vaporization it was, remember, over RT plus constant. That was the Clapeyron equation. And you see science repeats itself all the time. In that equation, you plot ln P first 1 over T in Kelvin, and you obtain delta H over R minus delta H vaporization over R from the slope. That was the business of homework 1. This is very simple, similar here. Here you plot ln Kr, which is the rate constant, versus 1 over T in Kelvin. Temperature must be in Kelvin. You should obtain a straight line that goes down on almost all the cases, and you obtain a slope that is equal minus EA over R, and then from that you can get the experimental activation energy for the reaction. So far so good. Any questions on the theory here? Now, what is the now here we have two. You can get two constants out of this fitting in Excel or any other program. The two constants you obtain is the EA, which is the activation energy of the reaction, and that you get it from the slope. You also get from the y-intercept, you get ln A, where from that you obtain A, which is called the pre-exponential factor. Pre-exponential factor, that means the term that is before the exponential, and that's what they call the pre-exponential factor. Now, this factor is actually a measure of the rate is which collisions occur irrespective of their energy. That's the book definition. But for me, I have also another meaning for it, another physical meaning. It tells you this factor tells you the nature of the transition state of the reaction, as I'm gonna explain in the next slides. So there are three things we can talk about in the Arrhenius equations. The first one is that the activation energy is given by the slope of a plot of ln Kr versus 1 over T, and that means the higher the activation energy, the stronger the temperature dependence of the rate constant. And that's meaningful. The higher the EA, the higher the dependence of the activation energy. I mean, the steeper the slope of the reaction. The other thing is the high activation energy signifies that the rate constant depends strongly on the temperature. If a reaction has zero activation energy, then it's independent on temperature. And that's very rare to have reactions with the zero activation energy, or we call them barrier-less reaction. In that case, the slope will be zero. Now, in very small cases, we get something what we call negative activation energy. And you see this girl having head spinning from the term negative activation energy, which does not make sense to any people, but actually it happens. And I'm going to tell you a personal story here about this negative activation energy. When I was doing when I was supervising a lady, her name is Zainab, a few years ago in Palestine. She was doing kinetic study on a drug, and when she brought me her results, she brought me the Arrhenius plot looking like this. She plotted ln Kr in her experiments versus 1 over T, and her data looks like this. And she of course fitted that into equation, and she said y is equal something minus 4,343x plus 11.2 whatever, and the r square was 0.99. And of course, as you know, as professors, we always say this is wrong, and there must be something wrong with your data, and we scolded her. And I start asking her a question like, did you change the temperature in Kelvin? She said yes. Did you do that? Did you do that? And she came up with the data again. I thought double checking she came up the next day after checking everything, and she came up with the same data. And I was surprised. I was like, what the hell happened here? This is a positive slope. That means the slope is equal to plus 4,300, 200 over R. And that means the activation energy in that case is negative. which is very, very rare and very, very unbelievable idea. So what I did, I went with her to the lab myself, and we repeated the experiments at different temperatures, and we found it's actually true. The Gail made no mistakes. She did what she has to do in the lab, and she did a beautiful job. And there was a part of the reaction, like was that, in fact, that we have a negative activation energy with a positive Arrhenius plot, and this is called anti-Arrhenius behavior. I know this is not your business, it's not part of the course, but just to tell you, there's something called anti-Arrhenius behavior, and actually we came up with an explanation for what's happening for this reaction, and we just published a paper. It's in a submission. It's in the publication stage here at one of the journals. And yeah, so anti-Arrhenius behavior or negative activation, it does exist, and it has some explanation. And the explanation for that is that the reaction must have some complex mechanism. It's not like a straightforward mechanism. Rather, it's a complex mechanism. It involves an equilibrium followed by formation of an intermediate. Okay. The other thing that you can use the Arrhenius equation, just like you use the Clausius equation, is you can obtain, without graphing, a one rate constant from the other at different temperature, using the very similar equation to the one we used for the Clausius. So here we have ln K2 over K1 is equal EA over R 1 over T1 minus 1 over T2. So 2, 1, 1, 2 with a positive. If you want to write this down, you can write this down in another form, as we always do, because you might have this equation written in different form. So it's always ln K2 over K1 is equal plus EA over R 1 over T1 minus 1 over T2. This is one form of the equation with a positive EA. You can multiply this by minus and you get ln K2 over K1 is equal minus EA over R 1 over T2 minus 1 over T1. So here 2, 1, 1, 2 with a positive, or 2, 1, 2, 1 with a negative. So this is the one that's written in the book. You might see this other equation in other books or in the internet, and they are both correct. It's just it's a matter of how you write the equation. So you can use this equation to just solve for K2 from different temperatures. I think this question came in one of the homeworks or one of the your exam. So I think this is a direct application for that. Let's try it. The activation energy of the reaction of citric acid cycle is this 87 kilojoule per mole. What is the change in the rate constant when the temperature falls from this to that? So we have a K, we have a rate constant. We don't have a rate constant. We have just two temperatures and activation energy. This is a change in the rate constant. So let's do that together here. I'm gonna actually do it on the same slide. Okay, so let me do it here as well. Already we wrote this equation. So the activation energy given is 87 kilojoules. So EA is 87 kilojoule per mole. T1 is equal and T2 is equal. So T1 we have 37 and T2 is 15. So we have cooling here. The action is cooling, and he needs a change in the K. So he's neither giving us K2 or K1, but he wants to change. So we write ln K2 over K1 is equal. Now EA is in units of kilojoule per mole and R is in joules, so we have to change that into joules, as you know. So this will be 87,000 joule per mole. Divided by R, which is 8.314 joule Kelvin minus 1, mole minus 1. times open bracket 1 over T1 minus 1 over T2. So K2 and K1, if you want to write this down, so T1 will be 37 plus 273. A few seconds here, I'm doing this for you guys. So this 37, 310 minus 1 over 288. So length K2 over K1 would equal to so this is actually length K2 over K1 and will come up to minus 2.72 minus 2, this whole term here. I just solved it in Excel minus 2.56, let's say 58. And therefore K2 over K1. I'm writing K as a capital. I shouldn't do that. I should write it as a small. So because of the difficulty writing on this screen. So this is K2 over K1 is equal e power this minus number, and if you just take the exponential, this will be exponential on this number, and that will be 0.070.075 or 6. Okay, 7. So K2 over K1, that's the change he's talking about, 0.076. And what does that mean is that when you reduce the temperature from 37 Celsius to 15 Celsius, that's not a big change, but it will affect this rate of reaction. So the value, the ratio of the second rate constant to the old one will be 0.076, and that means the rate constant will be reduced by this number. Okay, will be reduced by this number. I think this is the same answer we got here. Okay, you can flip this number if you want. So K2 will be reduced by that amount, or the ratio between K1 and K2 will be, if you are giving K1, you can calculate actually K2 from this value. Now the other question here is a graphing question, which should be also straightforward. The following reaction has studied at several temperatures, 2 and 203. I forget to tell you that the Arrhenius equation is just a general equation that applies to all rate laws. Doesn't matter, it doesn't have to be a first order or second order. So this Arrhenius equation, it's a general equation, okay, that can work for a zero order, first order, for any order of reaction. So it's not only for first order reactions. Now, so this is a question here that is giving you Kr, rate constant in the units of second minus 1. So this is first order, and we know it's first order from the units. There is nothing in the question that says first order, but we can figure out that it's first order from the units. And we have temperature in Celsius, and he's asking us to calculate EA for this reaction. Because of the fact that we have many values here, we can use graphing in Excel to do that. So we need to find ln Kr, we need to change temperature to Kelvin, and we need to find 1 over T in Kelvin. Then we plot ln Kr versus 1 over T to obtain the slope. So this is something we have done already for you. You can try this at home as well. And this is the temperatures in Celsius, which have changed it into Kelvin. So 20 Celsius is 293 Kelvin and so on. 1 over T would be a small number, and we listed that in Kelvin as well. And this is the K, and we have ln K, and you see how beautiful this table is formatted with nice significant figures and everything. Then we plotted this. We plotted ln k versus 1 over t. We got a very nice slope, straight line that is going down as expected, with the slope is equal minus 1.2 times 10 to the power 4. Usually the slopes of Arrhenius equations are big, okay, because they are in the units of joule. You get minus 4,000, minus 3,000, whatever. This one is even higher, minus 1.2 times 10 to the power 4. That's like minus 12,000 something. Now from the slope, he is not solving the part of the question, so let's do that. Now the slope is, so minus 1.2 times 10 to the power 4, that's your slope, which is equal minus EA over R, and therefore EA, the activation energy, is equal, the minus goes with the minus, of course, and you get a positive activation energy, which is equal 1.2 times 10 to the power 4 times R, which is 8.314. And if you multiply that, you get 9.98 times 10, 9.98 times 10 to the power 4 joule per mole. Now, why is that? Because, yes. Yeah, okay. So here, no, here, power 4, مش power minus 4. It's power 4, يعني 12,000, 12,000. So here, the slope of the Arrhenius equation is minus EA over R. Now, ln k has no units. Ln and log, as I always tell you, they have no units. 1 over t has a unit of negative 1. So this is something that is really important to understand, that the slope of the Arrhenius equation is in units of Kelvin minus 1. So this slope is Kelvin minus 1. Okay? So here, when you repeat this step and you put the units, it should be 1.2 times 10 to the power plus 4 Kelvin minus 1 times 8.314 joule Kelvin minus 1 mole minus 1. Sorry, I'm sorry. The slope is Kelvin. I'm really sorry. I made a mistake. This is in Kelvin, not Kelvin minus 1. Because when you plot where is that equation? It's appeared. Okay, when you plot ln kr versus 1 over t, the units of the units of your filling, the units of the slope, would be equal units of y over units of x, right? Because the slope is delta y over delta x, and therefore it's units of ln k, which is no units, okay, which is 1, I mean, divided by units of x, which is 1 over Kelvin, and that will give you Kelvin. So units of Arrhenius equation is Kelvin. But so we go back to our question here. I hope it's still there, okay. So the slope is in Kelvin times the R, which is 8.314 joule Kelvin minus 1 mole minus 1, and this Kelvin minus 1 goes with this Kelvin, and you get joule per mole. And that's why it's a big number, and usually we write this in kilojoule per mole, and we divide this by 1,000 to change it into kilojoule per mole, and that will give you 99.77 kilojoule per mole, which is a very reasonable activation energy. Activation energies for chemical reactions, they range between, let's say, 50 to 400 kilojoule. It could be higher, could be lower, but this is like a good range for activation energies for chemical reactions. You hear about the words 100, 200 kilojoule, 300 kilojoule per mole, 500 kilojoule, something like that. Okay. Now, in very small cases, you get negative activation energy, as I told you, and there is a reason for that. But in your book, I mean, most of the activation energies are positive, and that means the slope should be negative. Now, okay, so we solved this question. We solved that as well, and the final thing is that the final question here is that the Arrhenius, the pre-exponential factor. Now, before I go to the pre-exponential factor, is there any questions or anything that you don't understand, guys? Now, in this question, it says a rate constant is this decimeter cube mole minus 1 second minus 1 at 19 Celsius, and this 1.38 times the same thing at 37 Celsius. Evaluate the Arrhenius parameters and of the reaction. So we have two rate constants and two temperatures, and he says the Arrhenius parameters. Now, what does Arrhenius parameters mean? The word Arrhenius parameters means the activation energy and the pre-exponential factor. Okay? So this is example 3.36 in the book, 36.535 I mean. I'm going to solve it for you here, step by step. So K1 is 1.78. Let's just write what is given to us. Times 10 to the power 4, so 1.78 times 10 to the power 4. And this is in units of decimeter cube mole minus 1 second minus 1. Can anybody tell me what is the order here? Is it first order, second order, or zero order, or what? You can tell the units. What is it? Second order, yeah, because this is molar minus 1 second minus 1. This is second order, yes. 1.38 times 10 power 4, same thing. So K1 1.78 and 1.38. And this is at 19 and 37. So this is 19 Celsius. And this is 37 Celsius. Are 4 and minus 3. Okay, so this is a mistake. We have to be careful here. This is 10 to the minus 3. What's happening here is that the rate constant, this is minus 4 or 4. I just want to double check this question. Maybe there is a small typo on it, because the rate constant, when I increase the temperature, it actually decreases. And I just want to make sure that this is, I covered this question right from the book before we proceed, if you allow me here. Because I'm suspecting there's something wrong with this question. Okay, so what is happening? 335, right? 1.78 times 10 to the power 4 at 19 Celsius, and the rate constant, it actually decreases at higher temperature. This is interesting. Well, let's do it and see. I made no mistakes here. So he's asking to calculate the Arrhenius parameter, and this is something that actually you need to get familiar with in your chemistry classes and pharmacy classes. Arrhenius parameters, that means EA and A. Okay, these are the Arrhenius parameters. Because in the equation, Arrhenius equation, there are two things that are unknown: the activation energy and the pre-exponential factor. So we have to calculate both. So The way you do that, well, we have nothing but the Arrhenius equation. So we have ln k, say 2 over k1 is equal EA over R 1 over T 1 minus 1 over T2, right? So what we can do here, we have two temperatures, we have two Ks. We can calculate the EA from this. Okay, we can calculate EA from this. And what we can do after that, we can go back to Arrhenius equation and we calculate the pre-exponential factor A from the other equation. So let's do that. Because we have another equation that says ln kr, which is the mother equation, is equal A for E minus E over RT, right? So once we get the EA, we can plug it into this equation and use one of the KRs, either 1 or 2, and we put it here, okay? And we obtain the exponential factor. So here we have to use two equations. So the first step, let's do that. So first, to find the EA, we say ln K2, which is 1.38 times 10 to the minus 3 divided by K1, which is 1.78 times 10 to the minus 4 times 10 to the power 4, not minus 4, is equal to EA, which is the one we found, over R, which is 314, sorry, the one we need to find, I mean. I'm not writing the units here, but I'm sure that I will get an EA of units of joule per mole. And 1 over T1, so T1 is 19, so 1 over 19 plus 273, you always change to Kelvin, minus 1 over T2, which is the 37, right? So 237, sorry, 37. Plus, there's a lot of math to do here. So you find this 1 over that, and we've done this in the previous question. And this is all numbers here. This terms to the left is all numbers. You can evaluate that, and you can solve for EA. So I'm gonna do it in Excel, okay? And get back to you in 3 seconds. I have not done this question before, so I'm gonna do it again. I have not done it before lecture, so I'm just gonna do it again. This 1.3 E minus 3, and this is 1 point. So this is minus 16. This term is minus 16.37. This is equal EA over 8.314 times, let's calculate this term. And this is 0.0019. 0159, and this is Kelvin minus 1. Okay, so now we simplified that. So EA in this case will be equal to minus 16 times the 8.314 and times divided by that. Okay. So that will give you minus 85441. I'm just surprised it's minus actually. 85441. 441, okay. 0.7. And that's in joule per mole, okay. So let me open the answers. I don't know if you get the answers for chapter 6, guys. Let's just double check if we get the same the correct answer here before we move on. I hope that I remember Kauthar I gave you this the answer key for this chapter 635. We can move faster if we just click page down. It is positive here. Oh, okay. So you see here, this is what Atkins is usually. That's a problem of Atkins, okay? You see, he's saying -3, -4 in the answer key. And in the book, he says +4. Okay? And that was my surprise in the beginning. That's why even a textbook make a mistake. So the rate constant is something 10 to the power 4, and it's decreasing a lot when you increase the temperature. That means you have a negative activation. So I told you, so this must be -4 then. Okay? So I solved it based on the numbers in the book, and I get the right answer, which is -85. But it looks like there's a typo here in the book. Okay? And we changed that then. So please, in your slide, make this -4, just to make your life easy. Even though there is nothing wrong with the stuff we did, okay? There is nothing wrong with having a negative activation energy. It's just, you know, so please change this into -4 in your slide. Okay? Now going back to the question, we do that, we just change this into -4. Okay? You will get this as a plus. And because I'm doing this in Excel, it's easy for me just to fill the sum of this 1.78 E -4, and Excel will redo all the calculations for me. No, actually, it does not. It does not give me the same answer. So anyway, I will keep it as is. Okay, sorry. I will keep this as is, as a +4, and my answer is right. It's it's EA. It's minus, which is okay. Now let's move on, and just I want to show you. So to find the exponential factor, we apply this, that ln kr is equal a e power minus ea over RT. So based on the numbers that he gave me, -3 and +4, that's fine. I just got my activation energy. It's negative, so we go with that. Now we can use any of these information, either K1 at this temperature or K2 at this temperature, to find the A, because A is constant, right? It doesn't matter between the two Ks. So we're gonna use any of them. I'm gonna use the one with +4 and 37 Celsius. You can try to use it. So ln, what was it? 1.78. 1.78 times 10 to the power 4 is equal A e power minus EA. Now I have EA, which is minus 85. You see that? 441 joule per mole. I don't want to change it to kilojoule because the R at the bottom is in kilojoule, in joules. And that's very important to keep up with units. Since we accepted that it's minus, and there is a minus in the formula, it's minus. And this 8.314 times T, which is 37. 37 to be 310. So this is a number, this is a value, okay, we can find its unit, and this is also, all of this is in mathematics, so we can find A from that. So 1.78 equal 4, and that. Then that is 8 minus is 9.78. Len is 9.78. It's a big number, so it means that, so a positive, a big number has a positive len. That makes sense. This is equal A. Now this exponential equals 85,441 divided by 85,441 by temperature is 310. And 2 point, this is multiplied by 2 point, this is a huge number, which is fine, 2.49 times 10 to the power 14, okay? And this is a unit of what? Now watch the magic. Now this is in joule, mole minus 1, Kelvin minus 1. So this Kelvin goes with this Kelvin, the joules goes with the joules, and the mole, and everything. This is unitless, okay? This is very important here. Oh, by the way, I made a small mistake. I'm really sorry. This equation, there is no len here in it. Nobody corrected me. I'm really sorry. There's no len here, okay? It's KO equals K. Did I make a mistake? Yeah, sorry. I made a small mistake. There is no len. The equation is K1 is equal so and so. Therefore, this becomes as, so 1.7. 1.78 times 10 to the power 4 is equal A times this. Now this is unitless, okay? And I'm going to show you here. So this is 2.42, this is 2.49, 2.49 times 10 to the power of 14. And therefore A is equal, this times that, that will give you 7.13 times 10 to the minus 11. 7.13 times 10 to the minus 11. Okay. Now let's focus on the big picture here. First of all, in this question I found, okay. What is the question? Sorry, the question disappeared. Okay, let us focus on the big picture. We have two rate constants, okay? One is 4 and one is minus 3, and at two different temperatures. Now, there is a typo in the book, this should be minus 4, okay? Now, when we solve this question with the given numbers, we found EA to be around 85 kilojoule in the negative, and we found A as well in the negative. But if we do this the right way, and this should be in minus 4, then we get, let's say, an EA of 85 kilojoule and an A of the power of something to the power 11. Now, the thing I want to use really to, not to focus on the loss in details, is that this Arrhenius equation, which is K rate constant, is equal pre-exponential factor e power minus EA over RT. The EA that we found was, let's say, 85 was 85,441. Okay, and that's in joule per mole, right? Joule mole minus 1. This R is in units of joule mole minus 1, Kelvin minus 1, and this is in Kelvin. So this goes with that, these goes with this, and that means this term here is unitless. And this is something that is really important for you to understand. Since this is unitless, that means the units of A is equal to the units of R, of KR. And this is very important, something to remember. The units of the pre-exponential factor is the same as the units of KR. So the exponential factor that we found was 7.1 times 10 to the minus 11 if you depend. This is minus 10 to the minus 11, or it should be actually 7.1 times 10 to the plus 11 if we corrected the typo in the book. That should have, now what unit it has? This has the same unit as the K. It should be decimeter cube mole minus 1, Kelvin minus 1. Sorry, second minus 1. Okay, and this is something that is really important to remember, that the units of the exponential factor, a pre-exponential factor, is the same as the rate constant given in the question. Yes, sorry, go ahead. Which numbers? The units? Oh, I'm trying to find the units of K, of A. So here you have KR. Okay, we found the EA. Oh, you're talking about here. I divided them. I said A is equal 1.78 times 10 to the power 4 divided by 2.49 times 10 to the power 14. And I get something to the minus 11. If this is in minus 4, okay, and should be this in minus 14, then you plot this, you divide this by this, and you get plus 11. You have to solve the question, guys, girls. I'm just solving the question by myself. I'm making so many mistakes here, and I'm playing with it. I'm having fun this morning. But you should do this all by yourself from the beginning, okay? I advise. Well, the answer is 3.65 times 10 to the power 11 according to the book. This is the answer of the book, okay? He's just rearranging the EA to find, he's formulating a formula to find EA, R is equal this and this. He found EA to be 85, depending that he used this, you see that? He used the minus 4, not the plus 4. And he plugged it into the equation, and he found something. But this one he used the, yeah, okay. So please do this by yourself. Now, finally, we defined the activation energy at the beginning of this chapter to be the difference between the reactance and some state we call it the transition state at the top of this mountain here. So for reactants to go into products in any chemical reaction or any physical process, it has to go into this kind of a small hill. We call it activation energy. At the top of this mountain, you can write this in, like at the top here. I'm gonna draw it for you. This is called a transition state. Okay, and this answers the question why, for example, wood does not combust by itself. Now, when we bring some wood and when you heat it up or you give it a spark, it will convert into coal. It will combust. It will burn. But doesn't happen by itself because this needs that match or that lighter to give it some kind of heat, the initial heat where the reaction starts. And this is what the activation energy The activation energy is the little amount of energy that is required to initiate the reaction. Okay? The higher the activation energy, of course, the difficult for this reaction to happen. Now we imagine something we call a transition state. It's some structure between the reactants and products that the reactants should pass through in order to go to the products. And the energy difference between the reactants and this transition state is called the activation energy. And this has nothing to do with delta H of the reaction. Because delta H of the reaction, it's this difference between here to there. Delta H of the reaction, it's the amount between reactants and products, okay? Now, many people think that this is if you increase it, the activation energy, the delta H decreases or increases. And we said from the beginning of this chapter that these two has nothing to do with themselves, okay? The activation energy, it's a kinetic term that you obtain from a kinetic study and from rate constants. And delta H, you can obtain it from the heat, from Q, if you remember QP. That's thermodynamics. You go and do a calorimeter study or whatever, bomb calorimeter on all the business of chapter 1 in order to obtain delta H. So this is a thermodynamic term. Okay? The reaction coordinate is the collision of motions such as changes in intramolecular distance in the bond angles and are directly involved in the formation of products from reactants. The potential energy rises to a maximum, and the cluster of atoms that correspond to a reagent close to the maximum is called the activated complex. After the maximum, the potential energy falls as the atom rearrange in the cluster and reaction value characteristic of the products. The climax of this reaction is at the peak of the potential energy, which corresponds to the activation energy, and this is called a transition state. I know that you don't understand many of these terms, but I will show you a video of what's exactly happening in a reaction and what is a transition state. And from that, I can also tell you what is the meaning for me of the pre-exponential factor, as I promised you. But before we go into the video and so on, what does actually a catalyst do or an enzyme do? In this question, in this graph to the right here, you have the kind of the light line. This is the original activation energy for the original reaction. When you add a catalyst, the catalyst actually reduces the activation energy for the reaction. So if the activation energy is 100, when you add a catalyst, the activation gets lower to 60 or 50, and therefore the reaction goes faster, because the lower the activation energy, the faster the reaction. So a catalyst does actually two things. First thing is it actually introduces another pathway for the reaction. Okay, that's the first thing. Let's write this down in a new slide so you remember them. So the catalyst introduce another pathway, or we call it wave, route, if you like, for the reaction. So basically, it has another mechanism. Okay, a new mechanism for the reaction. That's the first thing the catalyst does. And from that, as a consequence, it lowers the activation energy. Okay? And the most important thing about the enzyme or the catalyst is that it should enter the reaction and exit the reaction without a change. So it does not participate in the reaction itself. It should, the definition of the catalyst, RXM means reaction. The definition of the catalyst is that it actually enters the reaction and exits from the reaction without affecting the reaction. So if you have reactants A that goes to B, okay? Let's say A goes to C, and then from C goes to D. A catalyst can come somewhere here, okay? A catalyst can can somewhere come here, but it has to exit from here without being changed. Okay? So, and the best, for example, this reaction, I think I told you about the N2 plus H2 produces ammonia. This is a widely, this is equilibrium, it might be complicated for you. Let's say that you have let's say that you have I can't come up with a good example here for you. Let's say CH4 plus O2 can go to methanol. This is an industrial process to form methanol, which is a variable added chemical from methane. This reaction is very difficult to do actually without a catalyst. But if you add a catalyst like Fe2O3 or palladium or whatever, palladium or platinum, whatever a catalyst, the catalyst enters this reaction, accelerates the process, it does it in different mechanism, and it exits the reaction untouched. So if you add 100 grams of this, of Fe2O3 to the reaction, you produce some methanol. That 100 grams, theoretically at least, it should not be affected with the reaction. So what does happen here actually? What does the catalyst means exactly? So let's say that you have here a hydrogenation reaction. Just I believe that you took organic chemistry, and you know what is this CH2, that's ethylene plus H2 goes to CH3, ethane. That's called hydrogenation reaction. So this can be happen in the gas phase. This is gas, this is gas, this is gas, which is very difficult to happen. But if you bring a catalyst, which is a metal surface, okay, let's say a platinum, maybe the H2 first will come close to the surface. It's called adsorption. It will absorb on the surface. It will break itself into two hydrogen atoms on the surface. Then this H will fly close to the surface into the gas phase. That's H atom gas by itself, H radical, and then it will attack quickly the ethylene, forming ethylene radical, and the reaction will continue. CH2, CH3 radical, and the reaction will continue. So this is how a catalyst works, and you can understand, of course, the enzymes. Many biological reactions that's happening in the human body, they're happening every second, and they're extremely difficult to take place by themselves. Maybe one reactant will will lock itself into the enzyme surface. There will be a reaction between the enzyme and that species, and from that it initiates steps into continue with the reaction on the enzyme surface, and the enzyme, of course, will unblock itself at the end from the reaction. So this is the definition of a catalyst. It introduces another pathway or another mechanism, okay, happening usually in the surface, and therefore it lowers the activation of the reaction energy, and then it will, and therefore it will speed up the reaction. So enzymes and catalysts are big businesses, even both at the industrial scales and in biochemistry, and there is so much study and so much research on how they work and so on. So that would be the end of this chapter, alhamdulillah, the kinetics chapter. I wish that you enjoyed it, and please continue with your project, and this is all the equations and this is the questions that you need to do. Now I promised you to show you a video of the transition state, so if you allow me to do that. So now, guys, I'm working on something we call computational chemistry, and in computational chemistry we study transition states, and we actually obtain kinetic data without even going to the lab, and it's a big field. And computational chemistry allows you to understand what is actually a transition state. So let me pull something here very quick for you. that I've done recently, let's say. Okay, so guys, let me start with this. You're taking organic chemistry, right? Or I mean, you finished taking organic chemistry. Anybody knows what is this compound called? Anybody? It's called cyclobutane, okay? So, now if I change this into silicon, it would be called diacylcyclobutane. It's a compound that I have worked on it during my PhD. There are, of course, H's attached, hydrogens attached here. Okay, so this is H2, H2, H2. Now in this compound, one reaction that can take place, this is called 1,2-H shift. Where this hydrogen travels here and the ring will open. Okay, and when you have a ring opening, will you have this becomes as CH2 and then SiH2, then CH2, and this will be SiH3. Okay, so it's a reaction anyway, and there is a hydrogen traveling from here. This is the reactants, and this is the products, and there is a transition state in between. There was a big fight between chemists how this actual reaction happens, and so on. So here I'm going to show you how we did this reaction in computational chemistry, and it's something we do all the time. So now this is this is the compound diacylcyclobutane. Okay, you guys are going to change the colors here for you to see the molecules. Colors. So silicon should be. Let's make it. Okay, so now this is the compound. It's called diacylcyclobutane. You have carbon, silicon, and this is the red one is silicon. This is carbon, and they make kind of a square. Okay, cyclobutane, 4 atoms, very simple molecule. There is a bond here in between, but it's not shown. This is called diacylcyclobutane. So this hydrogen here on the silicon, the reaction is that it travels or it shifts to the adjacent carbon. If this happens, then you will have a ring opening reaction. Now, this is something we're going to study in chapter, the next chapter, which is vibrations. And this is actually the transition state for this reaction. Transition state, it involves a vibration, that H is vibrating, trying to get to the carbon and getting out, trying to get to the carbon and getting out. You see, in and out, in and out. This is the transition state. This is maybe your first time in your life watching a transition state in work. Okay, this transition state, it's not the reactants, it's not the products, it's something in between. Okay, look at its structure. It's not like diacylcyclobutane itself. It's close to that structure. This hydrogen should be pointing there, by the way. But it's trying to come close to the carbon. Okay, and now if you look at the video of that, this is what we called this is the transition itself. See, see guys, what's happening here? It's a beautiful reaction. So what you see here is actually the products goes to reactants, which is the same thing. In computational chemistry, we don't differentiate between the reactants and products. We see the transition state to go from products to reactants is the same transition state that goes into reactants to products. So what you see here is that the hydrogen, it's traveling from the silicon to carbon. Okay, so from the carbon to the silicon. So at the beginning of this reaction, you have the products and you have the cyclobutane. So you have a reaction that is fully taking place in front of you. This is a beautiful thing about computational chemistry, is that this is something you cannot observe using any instrument. You can't say this by spectroscopy or lasers or UV vis or anything. Usually we see the reactants and products, and maybe something happen in femtoseconds or nanoseconds. But computational chemistry allows you to study these reactions in details, and this is just very simple reactions. Of course, we've done much complicated reactions than this. And this is the introduction of the computational chemistry, which big part of it is the drug design. And now you see people are fighting for their lives to discover a drug or a mechanism to cure COVID-19, and computational chemistry and drug discovery is in the heart of this. So what you see here is just a very start. This is like computational chemistry 101, which might lead you to study this more and dig in it and become a computational chemistry expert or computational biology expert, where you use this to discover new drugs and to treat diseases. So I hope that you now know what is a transition state. Oh, sorry, I didn't tell you what the exponential factor means. So now, the pre-exponential factor, the A, actually tells you the nature of transition state, if it's loose or tight. And what I mean by loose and tight, this transition state that you see in front of you is called a tight transition state, because this one looks like the reactants. Tight, يعني مضغوطة. يعني it's very close to the reactant side. This is called a tight transition state, and it's associated with the lower value of A, of the pre-exponential factor. If you have a loose transition state, that means it's open, okay, and its structure, it's far away from the reactants, then this transition state is associated with a high value of pre-exponential factor, which is A. And so the value of A itself tells you the nature, okay, or how your transition state might look like. So I hope that you enjoyed my lecture for the Arrhenius, okay. Please do these questions again by yourself. Just make sure to do them step by step and understand them. I advise you strongly to do this graphing here by yourself as well in Excel. Obtain AA from the slope. Obtain also A. We didn't solve for A, but this is something that you obtain the A for this. It will be in the units, of course, of the rate constant, which is second minus 1. This question you must do it again and change this 4 to minus 4 just to save your life. And this part as well, I wish you understand it. So by this we finished, alhamdulillah, chapter the kinetics. All of these questions you must solve them by yourself as well. The final exam, as you know, it will involve chapter 4, which is the equilibrium. This chapter 6, and also the spectroscopy, which we start on Wednesday, inshallah.